I want to put particular emphasis on this section of the lecture because the strategies, excuses, and tactics that deniers of global warming use are the same ones that were used by tobacco companies to sow doubt about the fact that cigarette smoke kills, same ones used to sow doubt that it was humans using CFCs that was destroying the ozone layer. Same ones used to sow doubt that it was pollution causing acid rain. And over the past 4 years, we have had a presidential administration that has waged war on science and the media and the voters by sowing disinformation, coming up with what they called alternative facts and outright lies. These tactics are used time and again because they work. Repeat the lies over and over, discredit the opposition, deny, resist, whatever. When people hear or read the lies repeated over and over, they begin to doubt their own ability to reason, attack the science by distorting it. And now, with the new administration's emphasis on mitigating climate change by reducing and one day eliminating our use of fossil fuels, the knives will be out. They will distort the administration's stance and then attack the distortion. For example, a scientist or a member of the administration will say in an interview, we want to wean people off fossil fuels. And the next thing you hear from a denier is, we will all be walking. They're taking our hamburgers away. Or we'll be living in caves. We're going back to the Stone Age. Another tactic is change the subject and talk about how unfair and unjust it is for John Kerry to fly on his own private jet. Like that is equivalent to the entire nation continuing to pump out greenhouse gases into the atmosphere. Oh, I get a little heated with this stuff. Okay, so let's look at some of these excuses and strategies here. Volcanoes, you hear this a lot. Volcanoes put out more carbon dioxide than is emitted from human activity. It's the sun. The sun is emitting more energy. That's why the globe is warming. Or, hey, China and India emit way more greenhouse gases than the US, so what good will it do if we reduce? Another one is, hey, scientists can't agree on anything. And then, of course, just sow doubt in the science itself. I like this little cartoon here. What if it's a big hoax and we create a better world for nothing? Well, first of all, it's not a hoax. My question is, why do humans have to wait until we're on the brink of a disaster before we make changes that will benefit us and benefit the earth? Here is the answer to that argument that volcanoes put out more CO2 than humans do. We're looking at CO2 emissions in metric tons here on the vertical part of the graph. And then this is since 1750 up to 2000. And we see that the pinky color line right here, the one that's steady as she goes, that's volcanoes. That's the volcano contribution to CO2. So you think we can outdo volcanoes? Oh yeah, look at this line. Up, 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 up. So that is a fallacy that about volcanoes. Humans by far put out more CO2 in the atmosphere. Let's revisit these concepts of climate feedback loops and radiative forcing. A positive feedback mechanism is one where the changes will reinforce the initial change. We already talked about Arctic ice melting, and when that melts, there's water. Water has a lower albedo, so it will absorb more solar energy, so the warmer water will melt more ice. That's a positive feedback mechanism, along with the permafrost in the Arctic regions melting. Permafrost is permanently frozen soil moisture. In that soil, you have organic material, And when the permafrost thaws out, that organic material, as it decays, it will release methane into the atmosphere. And methane is a greenhouse gas. So the warming that caused the thawing of the permafrost to begin with is also going to enhance the warming because the methane is released. Negative feedback mechanisms are those where the changes will reverse or offset the initial change. So if we have warming, then maybe we have a bunch of clouds. Clouds are hinky because some of them will reflect sunlight, some of them will absorb. So let's say we have those clouds that are reflecting sunlight, and that would tend to cool things off. So that would be a negative feedback loop that reverses the initial change, which was warming. And we looked at radiative forcing early on, where we're looking at the balance between the incoming and outgoing energy, incoming sunlight, insolation, and outgoing energy, heat. But there are these processes that will impact that balance. So the next graph looks at some of these climate drivers, as they're called, to determine if they result in warming or cooling. And the Milankovitch cycles would be an example of a natural driver. We discussed those earlier. And you have seen this, but I think it was turned the other way. So we're looking at natural processes that will result in warming or cooling of the atmosphere, and human activities. And we see that there are some things that cool, but by far what's happening is human activities are resulting in a net warming of the atmosphere. And one of the other excuses is China and India do it. China emits more than double what the US does in greenhouse gases. Well, but we have to remember some of China's emissions are from the production of goods that we benefit from here in the US. We buy lots and lots of stuff from China. And the US has been burning coal, oil, and natural gas for way longer than India and China have. We are 4% of the world's population, but we're responsible for 1/3 of the excess carbon that's heating the atmosphere currently. China, less than 1/6. China has 4 times as many people as the US, but they burn less than 1/2 as much fossil fuels as Americans do. We burn 10 times as much as a person in India. And the analysis by the climate action trackers suggests that China and India are on track to beat the targets they set in the Paris Agreement. We withdrew under Trump, but we're now back in. And the entire function of the Paris Agreement was to keep our temperature down below 2 degrees and hopefully at 1.5 degrees above average. There are some arguments that climate change could be based on sunspots because sunspots result in an increased output of solar energy. However, that isn't conclusive. There have been some links that have been made between sunspot activity and drought in the western part of the US using tree ring analysis. But what we do know is down here in the troposphere, which is the layer of the atmosphere where all weather occurs and where we live, and it goes up to about 10 miles, but it varies, it's variable, and it's varying now because of what is happening with temperature between the troposphere and the stratosphere. If it was the sun responsible for creating more heat on the Earth, then we would expect the troposphere and the stratosphere to warm up. The stratosphere is where the ozone layer is located. And remember what it does, it absorbs UV light. But what we're finding is that as the troposphere is warming, the stratosphere is cooling. And why is that? Well, the troposphere is warming because the Earth's surface is radiating heat away, right? And these greenhouse gases here absorb that and keep that heat, some of that heat that would be going up in the stratosphere, keep it locked in here. So we're warming, stratosphere is cooling. One of the other fallacies that is spouted out there is scientists can't agree on anything. Well, this is what disagreement looks like. These are the global average temperatures plotted from 1980 to 2015, and the global averages are calculated by, we've got 5 different entities here. The blue line is NASA, the green line is NOAA, the National Oceanic Atmospheric Administration. The red line is Hadley Met. They're sort of like the United Kingdom's NOAA. Then the purpley line is Berkeley Earth, and then Calton and Way are two guys that decided to go on their own and look at temperatures to see what they could get as a global average on a year-by-year basis. So this is what it looks like. Now, when you look at this, would you say that scientists disagree about what's happening to the temperature? The lines don't coincide exactly with each other, but look at the trends. Where you have a downward trend with one, you have a downward trend with all. Where you have an upward trend with one, you have an upward trend with all. So that is pretty good agreement. That would be cherry picking big time if you just picked one little section right here and said, oh, look at that, they're not agreeing. Well, they all show that there is a rise. Another argument you will hear is that this is the hockey stick graph, the one that shows temperature variations from the year 1000 to 2000. This is the famous hockey stick. I guess because it looks like a hockey stick, although I've never seen a hockey stick that has a, whatever that part of the hockey stick would be called, have one that big compared to the handle. But you will hear folks that will pick one little segment and they will talk about how there's been a decrease in temperature, totally ignoring this, the huge increase in temperature. So if you hear that argument out there, just remember this graph. Yes, you can look at this one right here. That's a downturn right there. Big deal. It doesn't matter. This is where we are now, and it continues to go up. Remember, this ended at 2000. All the warmest years have been since 2005, with 2020 being the warmest. This is the world famous CO2 curve from the Mauna Loa Observatory. Mauna Loa is in Hawaii. It's a high mountain, and there was a man by the name of Charles Keeling, and in fact this thing is called the Keeling curve, who back in 1957 decided that he wanted to test the breadth of the world. So he thought the best way to do that was put a CO2 monitor up where there wasn't a lot of industrial activity. So he went to the Pacific, to Hawaii, and established the first monitor there on top of the mountain. And he thought that it was broken because he didn't expect to see any variations at all. He thought it was broken, but turns out it wasn't. We're looking at two different things here. We see this solid black line. Let me get this. We see the solid black line here going trending ever upward, and we see the zigzaggy red line. Well, there are two things going, two different things, two different sources of CO2 here. The zigzaggy line is the seasonal response of vegetation. In the winter, when plants aren't growing and no photosynthesis is going on, then we would expect to see an increase in CO2. Summer, spring and summer, when we have plants that are blooming, crops that are growing, CO2 being used for photosynthesis, then we would expect to see a decrease in CO2. And that is what this is. That's what the zigzaggy line is, that's just the seasonal response of vegetation. The solid black line, humans. So the vegetation response is superimposed upon the human response. And again, this line shows no sign of stopping. Remember what the levels are right now, 415 parts per million. That will certainly go up. The Keeling curve. This is Mauna Loa. This is the top of Mauna Loa where those monitoring stations are, and they monitor for a lot more than CO2 here. I was here 4 years or so ago. I wanted to get an appointment to tour the place, but I left it too late and wasn't able to, so I had to stand outside the gate and just look in sadly, but I did get a picture. This is the global carbon budget for 2009 to 2018. And we look at where CO2 comes from, and it comes from fossil fuels and industry, and it comes from land use change, and those are the amounts right there. These are the units down here, billion tons of CO2. So there's 40.3 billion tons of CO2 going out into the atmosphere per year. Then there are also sinks. There are users of CO2 or carbon, and those would include plants, which of course have to have CO2 for photosynthesis, soil, and the oceans. The oceans absorb CO2, and as they do so, they are becoming more acidic, which is not a good thing because marine organisms have a certain temperature and a certain pH that they want to live at. So when those parameters change, it's not going to be good for these organisms. Already we have coral bleaching as a result of ocean waters getting warmer. The upshot is that there are about 18 tons per year of CO2 going out into the atmosphere. 2018 was a bang up year for CO2 emissions. Our emissions went crazy. Luckily, in 2019, they decreased somewhat. I don't know what the numbers are yet for 2020. This is a picture in Pennsylvania, and what you're looking at here could be termed industrial landscape. Every one of these pads that you see, these are drilling pads. This is once all the equipment is taken away, that there will be oil shale that's pumped out of these wells, and they are everywhere, just as far as the eye can see. This is a picture at night of the midsection of our country, the north midsection of our country, and we see Minneapolis lit up with, roads coming in and out. This is Chicago, all lit up. But this over here, this is in North Dakota, and North Dakota doesn't have any large cities like this. But look at that huge cluster of lights here. That's from drilling. That's from drilling operations, gas and oil. The Bakken is a layer of shale that produces oil and gas, and it's going great guns right now. So again, just adding more to the budget, adding more CO2 to be cranked out into the atmosphere. Climate change is happening, and the only question is whether it will be serious or catastrophic, and whether it will reach that point sooner or later. This graph shows the losses in billions of dollars from wildfires. The green line is inflation adjusted to 2018 values. And we see what is going on here. The last few years have outpaced all the other years in a huge way. and it will just continue because we no longer have a fire season. These fires can break out any time of the year, and it's because of the warming temperatures that just suck all the moisture out of the vegetation, so that all it takes is a spark and then there's a conflagration. Weather records here in the U.S. continue to be broken, not only in the U.S., but around the world. 2020 was the most active and the seventh costliest Atlantic hurricane season on record. There were 29 named storms, the most ever. We had to go 8 letters into the Greek alphabet for named storms. There were 16 separate billion-dollar weather and climate disasters in the U.S. There were 13 hurricanes, 6 of them major. 12 made landfall in the U.S., resulting in 409 deaths and $40 billion in damages. Hurricane Laura hit Louisiana. It had wind speeds of 150 miles per hour and a storm surge over 15 feet. Now, why is all this going on? Well, think about this. The temperature is warming. What causes weather? What's the fuel for weather? And it's water vapor. So the more the temperature goes up, the more water that's going to be evaporated into the atmosphere, the more fuel that's in the atmosphere. How much fuel? Well, think about Harvey. Harvey was in 2017, and there were 60.58 inches of rain that fell in one single storm. It was a 1,000-year event. Statistically, that means that rainfall like that should only happen once every 1,000 years, but it just seems to be happening more often now. Hurricane Michael that hit Florida in 2018 got upgraded to a Category 5 storm. That's the highest category that we have when we're looking at hurricanes. This is the small town of Mexico Beach on the Florida Panhandle that was just razed to the ground by the storm surge from Hurricane Michael, that Category 5 storm. Take a look at these maps and you'll see why the East Coast and the Gulf Coast are so vulnerable to these heavy storm events. This is the coastal plain, and they're very low elevation. So when these heavy storm events occur, the rain falls and it has no place to go, so it just sits there. Here again, you see the coastal plain here separated by the Piedmont coming around into Florida, Alabama, Mississippi, Louisiana, and into Texas. And then you also have barrier islands that are offshore, and they are also very vulnerable. They take the brunt of anything coming toward them from the ocean in terms of wind and in terms of high water. And then, of course, California. Look, we have a nice little inlet here into the Central Valley, which is just like a big bathtub surrounded by mountains on either side. So we're vulnerable to big storm events as well. This is one of those barrier islands off the coast of South Carolina. South Carolina has no climate plan to deal with rising sea levels. And also developers are able to just go crazy building on these terribly, terribly dangerous spots. As you can see, here's the ocean here, here's the bay in the background. So not a good place to be in a hurricane. Might be beautiful on a sunny day, but watch out. This is what happens in these lowland areas when these heavy rainfall events occur. This is the town of Nichols in South Carolina. About 400 people live here. They've been flooded 2 years in a row from hurricanes. And then these are islands in the Pacific. They are atolls, and they have very little elevation. This is Kwajalein Atoll. There's a big airstrip right there. There are research facilities here. There are tracking stations here. But can you imagine? This isn't going to last long when sea level gets just slightly higher. And then back here to the US, this was damage across the Midwest. I think this happened in August of last year. That caused $7.5 billion damage to crops and to the infrastructure for crops. These are grain silos that were just twisted by the wind. This was a derecho, which is a straight line wind, usually associated with very severe thunderstorms. Thunderstorms, if we have a big cumulonimbus cloud, thunderstorms have downdrafts associated with them that can hit the ground violently, and then they go out like that in a straight line. This is a cornfield that was damaged. These are trees that were snapped off. The leaves and needles just totally stripped away. Another weird sequence of weather was in September. Between September 28th and October 4th, there were 232 waterspouts over the Great Lakes. Then another outbreak happened between August 16th and 18th, where there were 88 waterspouts. That is a waterspout right here. They're kind of like tornadoes over water. And if there are any beer drinkers out there, I have bad news for you too. All the ingredients that go into beer, like barley, hops, and water, they're all in trouble as a result of global warming. I feel like Cassandra here, but there's more bad news. Alaska is warming up. The entire Arctic region is warming up faster than anywhere else. Average temperature for March, this was a year or so ago, recorded at NOAA in Barrow, Alaska. I'm going to call it Barrow because I cannot pronounce that name. Was 18.6 degrees Fahrenheit above normal. Fairbanks notched its first consecutive March days when the temperature never dropped below freezing. Ice roads built on frozen waterways, which if you've watched Ice Road Truckers, you know that that's only way that supplies can be brought into isolated villages and mining camps. Have become weak and unreliable. At least 5 people died that spring, not this spring, but a couple springs ago after falling through the ice that was melting sooner than it should. This is Portage Glacier Visitor Center in Alaska. They have these huge floor-to-ceiling windows here that, when this thing was built, used to look out on the glacier, but the glacier's been melting back. This is 1950. You see the glacier here, the terminus of the glacier here. This is 2002. The glacier's melted back so that now it's out of view of those beautiful windows. Here's another view of it. This is 1914. This is 2004. That's how much melting has taken place. There's the mountain. There's that same mountain. So the glacier is now back here. And that was 2004, so it's probably even further back. This is the tiny village of Yupik in Alaska. The entire village is having to be relocated because the thawing permafrost is causing everything to slide down here into the river. And you can see this happening here. So what do the climate models tell us? Future changes are estimated using the projections of the available data that we have, and all indicate accelerated warming. The IPCC estimates Earth's surface temperature will rise 2 degrees Celsius above pre-industrial levels by 2050, 3.7 to 4.8 by 2100. The rise rate will depend on how much CO2 and greenhouse gases humans emit in the future. This is something that is this 3.7 to 4.8 degrees. That is just something that is just hard to contemplate. The face of the world will be totally reworked if we get to that point. Hopefully we will not.